Current electricity. In current electricity, we study now about LR and CR circuits with DC source. How the current grows in an LR circuit? What is the mathematical relation that can explain such a growth? How the decay takes place? How can we explain mathematically? How to charge a condenser? What is the relation that can estimate the amount of growth and decay of current in an inductor? Growth and decay of current in an inductor. To study the growth and decay, first let us study the circuit diagram used for this purpose. It consists of an LR circuit. A resistance and an inductor are connected in series, and this series combination is connected across a source. Here DC source is the battery, and negative end of this battery is connected to the terminal P, two-way key. K represents two-way key, and for this two-way key, negative terminal of battery is connected and positive terminal of battery is connected to the resistance. Similarly, the positive end of the resistance is connected to Q, and the inductor is connected to the K two-way key. When the K key is kept in contact with P, then the source it creates current in the inductor. So the growth of current takes place in the inductor. When the key K is kept in contact with Q, then the inductor will be discharged. The current in the inductor will decay. So growth takes place when K is connected to P, and decay takes place when K is connected to Q. Now this is how the circuit works. Now let us pass on to the working of the inductor. How the inductor works. When the key K is kept in contact with P, the circuit is closed and the current passes from the DC source into the inductor. Initially the current will be 0. Slowly the current will increase. Slowly the current increases. As the current increases, then back EMF will be created. Back EMF will be created, and this back EMF increases with the growth of the current. The back EMF will increase as the growth of current increases. So this growth reaches to a value. The current reaches to a maximum value when the induced EMF becomes equal to the EMF of the source. When the induced EMF becomes equal to the EMF of the source, then the growth will be maximum current will pass through this inductor. Now let us derive a relation for the growth of current in an inductor. The current grows from the 0 value to the maximum value I0. At some instant t, after a time t, the current in the inductor be I. So the current becomes I in a time t. At that instant, the back EMF will be given by L di by dt, where di by dt is the rate of change of current at that instant. The effective current in the circuit is E minus L di by dt, where E is the EMF of the source. E is the EMF of the source, and the effective EMF is E minus L di by dt. According to Ohm's law, this effective EMF is equal to the potential difference across the resistance, that is Ri, where R is the resistance and I is the current in it. Therefore, from Ohm's law, we can write the effective resistance E minus L di by dt is equal to Ri. E minus L di by dt is equal to Ri. This can be rearranged as E by R minus L by R di by dt is equal to I. E by R minus L by R di by dt is equal to I. Let us define E by R as the maximum current I0. E by R is the maximum current. Let us indicate with I0. So the relation becomes L by R di by dt is equal to L by R di by dt is equal to I0 minus I. By substituting E by R as I0 and rearranging, we get L by R di by dt is equal to I0 minus I. This can be further rearranged as di by I0 minus I is equal to di by I0 minus I is equal to R by L dt. R by L dt. Let us integrate on both sides. We know that the current increases from 0 to the value I in time t. So the integral limits of current are 0 to I and the integral limits of time are 0 to t. Therefore, we get the relation integral 0 to I di by I0 minus I is equal to integral 0 to t R by L dt. Integral 0 to I di by I0 minus I can be written as minus log I0 minus I from 0 to I to the base E minus log I0 minus I 0 to I to the base E. This is equal to R by L t. R by L t. Taking minus sign to the right and substituting the limits, we get log I0 by I log I0 minus I by I0 log I0 minus I by I0 to the base E is equal to minus R by L t minus R by L into t. Or this can also be written as I0 minus I by I0 I0 minus I by I0 is equal to e to the power of minus R by L t. E to the power of minus R by L into t. Or by further rearranging, we will get the relation I is equal to I0 into 1 minus e to the power of minus R by L into t. This is the relation for the growth of current in an inductor. Interpretation of the relation for growth of current in an inductor. We have derived the relation for current in an inductor. The growth of current in an inductor is given with the relation I is equal to I0 into 1 minus e to the power of minus R by L into t. The relation for current is I is equal to I0 into 1 minus e to the power of minus R by L into t. We can also see the relation between the current and time by drawing a graph. The growth of current in an inductor can be observed graphically. Let us plot time on x-axis and the current on y-axis. If we draw the graph between the time and current, we will get an exponential curve as shown in the figure. The current in the inductor increases exponentially and it reaches the maximum value I0 in infinite time. The curve indicates that the maximum current will be attained in infinite time. By using the relation for current, we can estimate the current in the circuit at any time, at any instant of time. By substituting the value of time, we will get the value of current from the above relation. But for a particular value of time, that is when t is equal to L by R, when we substitute t is equal to L by R, we get I is equal to I0 into 1 minus e to the power of minus 1, that is equal to I0 into 1 minus 1 by e, which an estimation becomes I is equal to 0.63 I0. I is equal to 0.63 I0 when t is equal to L by R. That is, in time L by R, the current in the inductive circuit reaches 0.63 times the maximum current. That is, 63% of the maximum value of current is gained in a time L by R. This time L by R is termed as inductive time constant. Inductive time constant. and is expressed by 1 by lambda. L by R is expressed as 1 by lambda. From the graph, we notice that the current increases rapidly initially, but as time passes, the increase in current will be very, very slow. So it attains maximum current in an infinite time. Decay of current in an inductor. Decay of current in an inductor. The current in the inductor can be decayed by connecting K to the point Q. If K is kept in contact with Q, then the inductor gets discharged. The current in it decays. Initially the current is maximum, that is I0, and this current slowly decreases. The decrease begins as soon as K will be kept in contact with Q. Now the induced EMF opposes the decrease in current. So it opposes the potential difference across the resistance R. The decreasing current creates resistance, potential difference across the resistance R. So induced EMF, it opposes this potential difference. So the induced EMF is LdI by dt. And the potential difference across the resistance is Ri. So from applying Ohm's law, we will get minus LdI by dt is equal to Ri. By applying Ohm's law, or from Ohm's law, we get the relation minus LdI by dt is equal to Ri. Let us derive a relation, mathematical relation, for decay of current in an inductor. We have seen the relation minus LdI by dt is equal to Ri. From Ohm's law, we have shown that we will get the relation minus LdI by dt is equal to Ri. By rearranging, we will get di by I is equal to minus R by L into dt. di by I is equal to minus R by L into dt. The current changes from I0 to I in a time t, say, let us suppose the current decreases from I0 to I in time t, then by integration we will get, and the integration limits becomes I0, I and 0t. So we will get the relation integral I0 to I di by I is equal to minus integral 0 to t R by L dt, minus 0 to t integral R by L dt. So by integrating and substituting the limits of integral, we will get log I by I0 to the base e is equal to log I by I0 to the base e is equal to minus R by Lt, or I by I0 is equal to e to the power of minus R by Lt, or I is equal to I0 into e to the power of minus R by L into t. This is the relation that we get for the decay of current in an inductor. So the mathematical relation that can be used to study the decay of current in an inductor is I is equal to I0 into e to the power of minus R by Lt, minus R by L into t. Interpretation of the relation for decay of current in an inductor. We have derived the relation for decay of current in an inductor as I is equal to I0 into e to the power of minus R by L into t. We have defined a constant, inductive time constant, as lambda is equal to R by L. If we use this constant, we can write the above relation as I is equal to I0 into e to the power of minus t by lambda. We can study this by drawing a graph. This relation can be studied by drawing a graph. Let us plot time on x-axis and current on y-axis. And the initial current is I0 maximum. Then if we plot this graph, we will get an exponentially decreasing curve. An exponentially decreasing curve will be obtained. So from the current, from this graph, we notice that the current is decreasing exponentially. So the decrease is very large initially. The rate of decrease of current is very large initially. As time passes, the rate of decrease becomes small and small. the decrease will be less and less as time passes. So for complete decay, the time taken will be infinity. But we notice a particular case in which the decay current becomes a particular value. During the first decay constant time value, that is if t is equal to lambda. If t is equal to lambda, then we will get the relation I is equal to I0 by E. I is equal to I0 by E. That will be equal to 0.37 I0. 0.37 times I0. So the current will be decayed by 63%, or the remaining current will only be 0.37% or 37%, sorry, 37% of the initial value. The decayed current value will be 63% and the remaining current will only be 37% in one time constant time. Charging a condenser with a DC source. Let us consider the circuit used for this purpose. Here a resistance is connected in series with a capacitor, and the end of the capacitor is connected to the mid terminal K of double throw key, and the end of the resistance is connected to the positive of DC source, and the negative of the DC source is connected to the terminal P. Similarly, the end of the resistance is connected to the terminal Q. Now this is the circuit which can be used for charging and discharging of the condenser. If the terminal P is kept in contact with P, if the terminal K is kept in contact with P, then the capacitor gets charged. If the terminal K it is connected to Q, then the capacitor gets discharged. So the capacitor can be charged and discharged by using this double throw key. Now let us consider the charging process. When the terminal K is kept in contact with P, then the charging of the condenser begins. A current passes through the circuit because of the resistance, and thereby charge slowly accumulates on the condenser. As the charge flows onto the condenser, a potential will be developed across this capacitor. The potential across the capacitor opposes the potential which is responsible for the charging, that is the source potential. So the EMF of the source will be opposed by the potential difference created across the capacitor. Hence, the charging rate will be slowed down. The current passing through the resistance decreases slowly. So the condenser becomes charged. As the condenser gets charged, the current flowing through the resistance becomes less and less. So the charge flowing to the condenser also becomes less. So the charging rate becomes less as the condenser becomes more charged. When the condenser attains the potential of the source, then the current through the circuit becomes zero, then the condenser is fully charged. Let us derive a relation for the charge on the condenser while it is getting charged. Let E be the EMF of the source, and at some instant of time when the current through the condenser, when the current through the resistance is I, let Q be the charge on the capacitor. Let Q be the charge on the capacitor when the current I is flowing through the resistance wire. Since the EMF developed on the capacitor opposes the EMF of the source, EMF on the condenser is equal to Q by C, where C is capacity. So from Ohm's law, this difference of potential, the net potential difference EMF, will be equal to the potential difference across the resistance. So E minus Q by C is equal to Ri. E is the EMF of the source, Q by C is the potential difference across the capacitor due to the charge Q. Since this opposes the EMF of the source, so the net EMF will be E minus Q by C. This appears as potential difference across the resistor Ri. And this equation can be rearranged as EC minus Q is equal to EC minus Q is equal to RC into I. But I is dq by dt, rate of flow of charge. Hence, using dq by dt for I, we get the relation EC minus Q is equal to Rc into dq by dt. When the condenser is fully charged, the charge on the condenser is say Q0, then EC becomes equal to Q0 because the EMF or the potential difference of the capacitor becomes equal to E when it is fully charged. So EC becomes equal to the maximum charge on the condenser. So let us indicate it with Q0. Then the relation becomes Q0 minus Q is equal to Rc into dq by dt. Q0 minus Q is equal to Rc into dq by dt. This can be rearranged as dq divided by Q0 minus Q is equal to dt by Rc. Let us integrate on both sides. The charge increases from 0 to the value q, say in time t, then the integral limits becomes 0 to q for charge and 0 to t for time. Hence, the relation becomes integral 0 to q dq by q0 minus q is equal to integral 0 to t dt by Rc. Integrating and substituting the limits, we get the relation minus log q0 minus q divided by q0 to the base e is equal to t by Rc minus log q0 minus q divided by q0 to the base e is equal to t by Rc. By rearranging this using mathematics, we will get the relation q is equal to q0 into 1 minus e to the power of minus t by Rc. Therefore, q is equal to q0 into 1 minus e to the power of minus t by Rc. This is the relation which is used for obtaining the charge on the interpretation of the relation for the charging of a condenser. The relation for charging of a condenser is obtained as q is equal to q0 into 1 minus e to the power of minus t by Rc. If we draw a graph between time and the charge, we get an exponential curve because the condenser will be charged exponentially. So let us plot time on x-axis and charge on y-axis. Then the relation, the graph that will be obtained will be as shown in the figure. Q0 is maximum charge. That maximum charge will be attained in infinite time. From the graph, what we notice is initially the charging rate is very high, but as the charge increases on the capacitor, the charging rate decreases. Hence, it takes infinite time to charge the capacitor fully. Let us consider the special case in which in time t is equal to Rc, in time t is equal to Rc, we notice from the above relation q becomes equal to 0.63 q0. By substituting t is equal to Rc in the above relation, we will get q is equal to 0.63 q0. Let us indicate or let us name Cr as time constant of CR circuit. Cr as the time constant of CR circuit. In the first CR time, during the first time constant time, the charge accumulated on this condenser is 63% of the maximum charge. So initially in a time constant time, it gets charged up to 63% of its maximum value. Discharging of a condenser. The discharge begins when the terminal K is kept in contact with Q. When the terminals K and Q are kept in contact, the discharge of the condenser begins. Initially, the rate of discharge is very high, but the discharge rate decreases as the time passes on. Here, the PD across the condenser drives the current through the resistor. The potential difference across the condenser drives the current through the resistor. As the charge decreases, the potential difference across the condenser decreases, hence the rate of flow of charge will also decrease. The driving rate decreases, so the current decreases. So it takes infinite time before the condenser is fully discharged. Let us derive a mathematical relation for the discharge of a condenser. After starting the discharge, after a time t, let Q be the charge on the condenser. The charge left on the condenser after a time t is, say, Q. Then the potential difference on the condenser is Q by C. This potential difference drives the current. So from Ohm's law we can write minus Q by C is equal to Ri. Minus Q by C is equal to Ri, where R is the resistance, I is the current through the resistance. But I is equal to dQ by dt. So the relation can be written as minus Q by C is equal to R dQ by dt. Minus Q by C is equal to R dQ by dt. Rearranging this, we get dQ by Q is equal to minus dt by RC. Let us integrate both the sides. On the left side, the initial charge is Q0, and after a time the charge becomes Q. So the charge changes from Q0 to Q, whereas the time changes from 0 to t. So the relation can be written as integral Q0 to Q dQ by Q is equal to minus 0 to t integral 0 to t dt by RC. So by integrating and substituting, we will get log Q by Q0 to the base E is equal to minus t by RC. Log Q by Q0 to the base E is equal to minus t by RC, or Q is equal to Q0 into e to the power of minus t by RC. Q is equal to Q0 into e to the power of minus t by RC. This is a relation that can be used for finding the charge on the condenser after a time t, while it is getting discharged. Interpretation of the relation obtained for discharge of the condenser. The relation that is derived for the discharge of the condenser is Q is equal to Q0 into e to the power of minus t by RC. This is an exponential relation. If we draw a curve taking time on x-axis and charge on y-axis, we get an exponential curve, exponentially decaying curve. But the initial charge is Q0. The curve, it approaches the time axis, x-axis, but it will never meet the time axis. If we put t is equal to RC in the above relation, if we put t is equal to RC, we get Q is equal to 0.37 Q0. Q is equal to 0.37 Q0. That means the charge after a time t is equal to RC is 0.37 times the initial charge. That means the remaining charge is only 37% of the initial charge. So the condenser loses 63% of its charge in one time interval. In time CR, it loses 63% of the charge, and there remains 37% of the charge only. But for complete discharge, it takes infinite time. Initially, the rate of discharge is very high, but the rate of discharge decreases as the condenser gets discharged. For quick discharge, the time constant should be very small. Summary of this class. If an inductor and a resistance are connected in series across a battery of EMF E, then the relation between the EMFs and potential differences is E minus L di by dt is equal to Ri, where I is the current in the inductor. The current at any instant is given by I is equal to I0 into 1 minus e to the power of minus R by L into T. I0 is maximum current and R by L is known as inductive time constant. In one inductive time constant value, the current, in the first inductive time constant value, the current grows to 63% of maximum current. So 63% of maximum current is attained in the first inductive time constant time. During decay, the current at any instant I is given by I is equal to I0 into e to the power of minus R by L into T. In the first inductive time constant L by R time, the current decays by 63% and the remaining current will be only 37%. Both growth and decay are exponential. The growth of charge in a capacitor is given by the relation Q is equal to Q0 into 1 minus e to the power of minus T by RC, where RC is called capacitive time constant. In the first time constant time, the current grows to 63% of its maximum charge. Charge. The charge grows to 63% of its maximum value. The decay of charge is given by the relation Q is equal to Q0 into e to the power of minus T by RC. In the first time constant time, the charge decays by 63% and the remaining charge is only 37%. Both charging and discharging are exponential.